Now, consider the observable universe as a sphere extending outwards from any observation point for 46.5 billion light years. The farther away we look, the farther back in time and more redshifted the view becomes. This raises a captivating question. What is the shape of the universe?
Well, one point is that it's expanding and we always see the same radiation out there, so the glow of the Big Bang. But there are some deeper reasons. From the theory of inflation, the best way to explain the universe, the properties that we see, is that it's very much bigger than the piece we can see. So, for example, we measure space to be what's called flat. So if you imagine slices of space, let's imagine slices of them at different times. So you just slice the universe, and it can have a geometry, right? It can be flat like a tabletop, or it could be curved like a sphere, or it could be curved in the opposite direction, sort of like a saddle or a bowl. And we can measure that. And when we measure it, we see it's absolutely flat. And that's a very unusual thing for it to be like, because what Einstein's theory says is that the shape of space, that the curvature of space is determined by the stuff that's in it. That's basically Einstein's theory of general relativity. Put stuff in space and it curves it and bends it and warps it and stretches it and so on. And what we find is that there's precisely the right amount of stuff in the universe to have a completely flat universe. And the explanation, the most favoured explanation for that, is the universe is way bigger than the piece we can see. And that's one of the ideas about the universe and why it appears to be the way that it is, because it's way, way bigger. So we're just looking at a little piece, and that's why it looks flat.
But what shapes the very fabric of